Exponential functions. The exponential function with base a, and in this definition a is supposed to be a positive number different than 1, is defined for all real numbers x by the following recipe. F of x is equal to a to power x. Okay. Once again, the base must be a positive number and different than 1 for that thing to be an exponential function with base a. Let's take an example. Which of the following functions are exponential functions? Let's talk about part 1. It's a function v that takes input x and outputs negative pi to that power x. Well, this function is not an exponential function because the base here is negative pi, and that base, technically you are comparing it to a here in the definition, is not a positive number, correct? So the base is not a positive number. As such, this is not an exponential function. So here, no, it is not, since negative pi is not positive, right? In fact, it's negative. Part 2. Function t takes inputs x and outputs pi to power x. So the function outputs pi to power x. It is of this format, and the base is positive and the base is different than 1. Remember, pi is not 1, right? It's 3.14, etc. It's an irrational number that's not anyway, so it's an irrational number. Certainly it's not 1, and as such this is going to be an exponential function, correct? So yes, since pi verifies the two conditions for the base, right? So verifies that it's a positive thing and it's not 1, right? Correct? How about w? The function w. The function w, it takes input x and outputs the product. This is a product here, right? So the product between x and pi, the input and pi. Well, it's not of this format. Here I'm taking the input as being the exponent to that fixed base a, right? So this is certainly, w is certainly not an exponential function, correct? So no, because it doesn't have this format, correct? Okay. And part 4, p of x is equal to x to power pi. P of x, so p of an input is equal to the input to the exponent pi. Contrast it with this. F of x, the exponential function with base a, right? F of x is equal to the base, which is already fixed, to the power that input. Make sense? So in the exponential function, the base is frozen, right? I mean, you just freeze that number, and you whatever you input, that input sits as an exponent. Whereas p, you're freezing the exponent and you are letting the base to vary, and in fact it's taken, so the base is actually the input of that function p, right? So certainly this is not an exponential function because it doesn't have this format, right? It's not a frozen base to the variable which is the input of the function. Okay, so this is not an exponential function. Okay. The graphs of exponential functions. So remember, the base of an exponential function has to be a positive number different than 1. As it happens, there are two trends for the exponential functions depending on the base. If the base is between 0 and 1, then the trend looks like this, the blue one. And if the base is bigger than 1, then it's going to look like the pink one, the pink trend. For example, if you take the base to be 2, I'm expecting the trend to be like the pink one, because the base is 2 bigger than 1. Let's take points on the graph of the function 2 to power x. If x is 0, 2 to power 0, non-zero base to power 0 is 1, right? So the point 0, 1 is going to be part of the graph. Remember, every point on the graph looks like x f of x, right? Input, comma, the output through the function of that input, right? So every point on the graph looks like x f of x. So this function, every point here looks like x a of x, correct? So every point on the graph here looks like x comma f of x, which is a to power x. Well, if the input x is 0, the output is going to be a to power 0. We were talking about a being 2, so 2 to power 0 is 1, right? How about if the input is 1, so and the base is 2? This becomes 1 comma 2, right? 1 comma 2 to power 1, so 2. So 1 comma 2 is going to be on the graph. If x is 2, becomes 2 comma 2 squared, so 2 comma 4 is going to be on the graph. And 3 comma 8 is on the graph, right? Because 3 comma 2 to power 3, 2 to power 3 is 8. 4 comma 2 to power 4, so which is 16. So 4 comma 16 is on the graph of the function a to power x, right? And so on and so forth. And I hope you start realizing that the function is blowing up quickly. It's blowing up very fast. It's kind of going to infinity very fast. I mean, to see this, for example, consider the function y equals x. How do you graph the line y equals x? It's just a line that goes through the origin like this, right? For example, the point 1, 1 is on the graph, correct? And here we're talking, let's say, about 2. So 1 comma 2 is on the graph of the exponential function. Start seeing that this is faster, growing faster than the line, correct? This is why it's part of everyday's language now. People say things are growing in an exponential fashion, right? So they're kind of like growing very fast. Yeah, anyway. Okay, so let me just erase this part. Okay, and if x is less than 0, let's keep talking about 2 to power x. If x is less than 0, how about taking x to be negative 1/3? So the point negative 1/3 comma 2 to power negative 1/3 is going to be part of the graph of 2 to power x, right? It's going to be somewhere here. Well, what do you know about this number? What can you say about 2 to power negative 1/3? Well, this number is 1 over 2 to power 1/3. Am I correct? So this is 1 over the 3rd root of 2. Correct? Okay. And what can you say about this whole quotient then? It's smaller than 1. And I mean, it's small, right? It's smaller than 1. It's positive, certainly positive, and smaller than 1. Correct? What if I change this exponent to be like negative a million, meaning I'm going to location negative million, somewhere here, let's say, and the output is going to be 2 to the power negative a million, correct? So let me adjust this writing here. So if I go to location negative million, the output is going to be 2 to the power negative a million. Am I correct? My point now is, let's check this number. Well, this number is 1 over 2 to the power 10 to the power 6. So 1 over 2 to the million. Correct? What can you say about this number? This is a small number, and it's also a positive number, right? So this is closer to 0 than when the input was negative 1/3, let's say. But the idea is the output remains a positive number. And I mean, is there a way to plug in something, a negative number, let's say, so that this green thing becomes 0 or less? Well, no. If you take an asterisk here instead of 10 to the power 6, this becomes negative asterisk. So 2 to the power negative the asterisk is the same as 1 over 2 to the power the asterisk. Am I correct? Whatever the asterisk is, that guy is a positive number, right? Because 2 to the power the asterisk is positive, and 1 is positive. Positive divided by positive remains positive. Correct? So the idea is this function, I mean, this point is part of the graph of the function, and that y coordinate is a positive number. So certainly it will never, and this is for all asterisks. So this trend, this graph never reaches the zero, the ground, the x-axis. There's always a threshold in between the two, right? This value, and hence the point, is certainly above the x-axis because of this observation, right? Okay. So this is why the function as x becomes large negative, in other words, as x goes to negative infinity, this trend kind of like goes to 0. They kind of hug each other but never touch, right? They hug each other. The pink graph becomes very, very close to the x-axis but never reaches it because of this observation. Okay. A similar discussion when a is between 0 and 1. Think about a like 1/2. Try to plot numbers. You're going to see a trend similar to this. Now this time around, the function or the graph of the function is going to hug the x-axis towards negative infinity, towards plus infinity, right? When x becomes large, the function is getting closer and closer to 0, right? It's going to still pass the y-axis. It's going to still have a y-intercept at 0, 1. Because if the base is a number that's not 0 in this case, and you raise it to power 0, non-zero to power 0 is 1. So no matter what a is, this is always passing through 1, correct? And it's gonna come like this. It's a decreasing function when a is between 0 and 1. And it's an increasing function when a is bigger than 1. Okay, it blows up as x increases, as x goes to infinity. The pink one, here it blows up, the blue one blows up as x goes to minus infinity. And for the pink one, as the input x goes to negative infinity, the function goes to 0. And for the blue one, when a is between 0 and 1, if x goes to plus infinity, as x becomes large, the function goes to 0, right? It will never reach 0, but we can see that it's going to 0, right? It's kind of like going towards the ground. That's what I mean. The height is becoming 0. Okay. All right, so let's see this comment here. the function ax, no matter what the base is, as long as it's positive and and different than 1. So it's going to have either the pink trend or the blue trend. In both cases, the domain of the function is all real numbers, right? Imagine you try to flatten any of the two graphs along the x-axis, you're going to see all of the x-axis, hence the domain is all real numbers. And the range of any of the two, again, the range is about the collection of all the possible outputs through the function, right? Let's think about flattening the function, the pink or the blue, along the y-axis, which means we're going to try to project all the points on the graph, the pink or the blue, onto the y-axis. You're going to see the positive side of the y-axis, right? So the range is 0 to infinity, open at 0. Okay. And the line y equals 0, which means the x-axis, we're talking about it, it's referred to as a horizontal asymptote of the function. Horizontal asymptote in the sense that the distance separating the axis and the graph decreases, right? Decreases. Look, you see the distance between the two? It's shrinking, am I correct? Right? The distance is shrinking, it's going to 0. And similarly here, the distance is shrinking, right? As such a line is referred to as an asymptote, and because this is a line that's horizontal, we're gonna say it's a horizontal asymptote. And the reason is, as I explained before, as x goes, when a is bigger than 1, when we are talking about the pink graph, as x goes to minus infinity, the function ax goes to 0, right? The distance between the graph and the x-axis decreases all the way to 0. And when the base is between 0 and 1, the function goes to 0, but now when x goes to plus infinity, right? When x becomes large, the x is the input. When x becomes large, the y values of the function decreases all the way to 0. Make sense? Okay. All right, let's do a few problems. Let's go to the book. And this is section 3.2, page 376, PDF 403. All right, let's choose a problem from 23 to 32. How about 28? So let's see the question. The question is, it has 3 parts. Use transformations of the graph of y equals 3x and y equals 4x, 4 to power x. By the way, how do you graph in this case we have 4 to power x. How do you graph 4 to power x? Which trend is it? Well, 4 to power x, the base is 4, right? It's bigger than 1, so the trend is the pink one, the pink trend. Am I correct? The pink trend. So we know how to graph 4 to power x. Now we want to try to graph the graph of qx, which is 4 to power x plus 1 plus 2. This is part A, correct? Let's do it. So 4 to power x plus 1 plus 2. Okay, so this is what page again? Let me zoom in a little bit. Page 377, as we said. And this is number 28, right? Okay, so we have the function q of x. We have the function q of x is equal to 4 to power x plus 1 plus 2, right? Okay. Now we're gonna start from the parent function in this case, which is 4 to power x. And we said 4 to power x, since the base is bigger than 1, it's gonna look like the pink trend, right? It's an increasing function. right? It's an increasing function. So let's call this parent function p of x. So p of x is the parent function 4 to power x, and we know how to graph it, right? It's just this function that we had above. This is p of x. The y-intercept happens at 0, 1, right? So this height is 1. Okay, and I want to transition from this parent function all the way to q of x by doing one transformation at a time, right? This is the instruction of the question. Okay, so either we add this 1 or we add the 2. It doesn't matter, the steps are commutative. Let's add the 1. So let's create let's call a function. Let's call it k of x, the function 4 to power x plus 1. And I would like to find an algebraic relationship between k and p, right? So what is this guy in terms of p? This is p of x plus 1, right? Why? Because look what p does. P of the input is equal to 4 to the power that input. Well, what do I have here? 4 to power x plus 1. So this guy better be the input in p to get that as an output, right? Okay, so this is the relationship between k, algebraic relationship between k and p. K of x is p of x plus 1. And how does this translate at the level of geometry? Well, we gotta shift the graph of p, right? We know how to graph p. The question is, how do we graph p of x plus 1, which is k? Well, we gotta shift the graph of p, it's a horizontal shift, by 1 to the left, right? So we're gonna shift this graph by 1 to the left. And we're gonna get a similar graph. The trend is gonna be similar, right? Oops. So that's k of x. But the that point used to be here at the time, right? It used to be here. It's 1 unit. It was 1 unit ahead, right? So we gained a moment in the future in some sense. So that point now is gonna be over here, and this used to be for input 1 at the time, right? So for input 1, now it's gonna be for input 0. And for input 0, this is going to be how much? 4 to power 0 plus 1. What's 4 to power 0 plus 1? Well, 4 to power 0 plus 1 is 4 to power 1, which is 4. So that height is 4. You can check it here. When the input was 1, this height was 4, right? Correct? So now, since we're shifting this graph 1 unit to the left, so that point is going to become the y-intercept, and that's what you're saying. But now it's going to occur at moment 0. Correct? Okay. Finally, I cooked up this term. I still have to cook up the 2 in order to get to q, right? So now I can get to q from k, which I know how to graph. And q is simply k of x plus 2. The output of k plus 2, if the input is the same as x, plus 2, right? So that's the algebraic relationship between q and k. Now, do we know how to graph k? Yes, it's the blue one. And as such, we're going to be able to graph k of x plus 2, which is q, because by one of the transformation we learned in earlier sections, it's a vertical shift now, right? You're adding to the output of k something. So it's a vertical shift by 2 units upward, correct? So we're going to shift this function 2 units upward. And we're going to obtain something like this. All right, so this is the function q. And this intercept now is 6, right? Right, so because q of 0 is k of 0 plus 2, and k of 0 is 4, right? So 4 plus 2 is 6, so you can recheck it. Furthermore, remember the function p had the horizontal asymptote y equals 0, right? Let me graph it for you in a different color. How about the red? So this line here, that's the y, the what is it? The horizontal asymptote, correct? This is what we said over here. So the line y equals 0 is the horizontal asymptote. In this case, when x goes to minus infinity, right? The function decreases to 0. And that line, so which is y equals 0, that line over here, what did we do to get q from p? We shifted horizontally, right? So that remains the same. So that line remains the horizontal asymptote, because what we did here for p to get to k is we just shifted the graph of p horizontally. So we took this guy and shifted horizontally. That horizontal axis or that asymptote, horizontal asymptote remains what it is, right? The function k remains, I mean, it's still getting to 0 as x goes to minus infinity, exactly like p, right? But still, p is slower 1 unit, just 1 unit of time in some sense, correct? But towards negative infinity, the two functions are kind of like going to 0. But to get to k from to get to q from k, what did we do? We took this graph k and we shifted up by 2. And if you shift it up by 2, its horizontal asymptote also has to be shifted by 2, right? I mean, the whole thing is shifted by 2. So the points here of the function k decrease all the way to 0. Now if those points are decreasing to 0, then the points on q are gonna decrease to 2, right? So that horizontal axis, or that horizontal asymptote, now is at height 2. Make sense? Does this make sense? So I'm talking about this horizontal asymptote to be now at 2. One more time. If the points of the graph k decrease to 0 when x goes to minus infinity, if you shift the whole thing by 2, so those guys are going to 0 as x goes to minus infinity. So those guys, the q guys, are going to 0 plus 2 in some sense. So they're going to 2, they're decreasing all the way to 2, right? All right, so anyway, so we're going to need this in the future parts of this problem. But the graph of q, there it is, or something like this, right? With a grain of salt, obviously. Okay. Let me go back to the questions. The questions, or the second part, was write the domain and range and interval notation of this function q. So part B, domain of the function q. Well, if you try to flatten the graph of q along the x-axis, that's the x-axis, right? If you try to flatten the graph of q along the x-axis, or in other words, if you try to project orthogonally all the points of q onto the x-axis, you're going to see all of the x-axis, right? Every element of the x-axis has an image through q. I mean, this function keeps going this way, keeps going this way. Every point on the x-axis is going to have an output through q. So the domain is going to be all real numbers, right? How about the range of the function? Range has to do with the collection of all outputs, right? Through the function. Well, take a look at the function q. What are all the y values that the function can produce? Well, those guys are gonna decrease all the way to 2. Never touch the 2, because the function p originally never touched 0. So that behavior is gonna we're gonna carry it over by translations, right? By doing the transformations we did. So those points will never reach 2, and they're gonna reach all the levels above 2, right? So the function produces outputs that are bigger than 2. In other words, if you try to flatten or project all the points of the graph or on the graph of Q onto the y-axis, you're gonna see the part of the y-axis that's beyond 2. Make sense? All right, so the range of the function Q is 2 open to plus infinity. Okay. And finally, part C, write an equation of the asymptote. Well, we've already done that, right? It's the line y equals 2. So y equals 2 is the horizontal asymptote. And we discussed this above, right? Okay, let's keep going. Let's go to a new problem. Let's go to the next set. How about a problem here? How about 36? Use transformations of the graphs of y equals 1 over 3 to power x and y equals 1 over 4 to power x. In this case, we're going to be needing 1 over 4 to power x to graph the given function. The function is negative 1 over 4 to power x minus 2, right? So this is number 36. So we have h of x equals negative 1 over 4 to power x minus 2. We know how to graph the function 1 over 4 to power x. This is the function we're going to start with. It's used to be the blue trend, right? The base is 1/4, which is between 0 and 1. So it's the blue trend. It's the descending trend, or the decreasing trend. Okay, so let's start with this as our parent function. So that's going to be our p of x, let's say. 1 over 4 to power x. And the function looks like this. Right? So this is the function p. Very good. Remember, y equals 0 is a horizontal asymptote. Okay, next. I'm going to either inject this minus or the minus 2. One or the other, doesn't matter, as long as you do it correctly. Let's say let's inject this minus. How about we call the function w of x, this intermediate function, which is negative that term 1 over 4 to power x. Remember, I'm cooking up this term, right? I'm cooking up this term. I'm injecting this minus. That's an algebraic thing. I want to find the relationship between this expression and p. In other words, I want to find the algebraic relationship between w and p, right? I want to transfer information from p to w. And to do so, or between the graphs, I should say. To do so, I want to find the algebraic connection between the two first. Well, this term looks to me like p of x. So it's not hard to observe that w of x is negative p of x. Correct? For all x. How do you graph the graph negative p of x? Now the geometrical aspect. How do you graph negative p of x if you know to graph the function p of x? Well, you just reflect the function p in the x-axis, right? That minus 1. You're multiplying the output of p by minus 1, which means you're reflecting geometrically, you're reflecting the graph of p and the y-axis and the x-axis. So we get, this is the x-axis now. So we get something like this, right? Agree with me? This is the function w. Okay. And finally, I still have to cook up the minus 2 term. How about, I mean, the name is h anyway, so h of x is going to be, h of x is going to be all this guy, right? And this guy by itself is w of x, no? So one more time, in h, this guy, we refer to it as w of x. So that's going to be the w of x minus the 2, right? Minus the 2. Okay. We know now the algebraic connection between h and w, and we know how to graph w. This is the graph of w. Now I want to transport this information, or transfer this information to h. Well, you just shift it down by 2, right? You shift the graph of w down by 2 because of this algebraic connection. And shifting that graph down by 2, the values which used to tend to 0 as x goes to plus infinity, now they're going to tend to minus 2 as x goes to infinity, right? They're going to approach now negative 2 because you're shifting everything by 2 down, right? So we're going to get, let me once again color this line, the horizontal asymptote, in red. It remains here, right? Because we did the reflection in the x-axis. So that line is its own reflection with respect to itself, right? Okay. And over here, it's going to be at negative 2. We're shifting down by negative 2. So that line now is going to be at negative 2. And the function w is going to look like, is going to look something like this, right? Oops. Something like this. So that's the graph w. What's the y-intercept? Okay. What's the y-intercept? Let's go back to find the y-intercept in P. Well, this y-intercept was 1, right? This y-intercept was 1. The y-intercept here is negative 1 because we reflected in the y-axis. And the y-intercept here is going to be what? We're shifting down by 2. So minus 1 shifted down by 2. Subtract 2 from this number. This is minus 3, right? So you get this. If you want to recheck if the y-intercept is correct, just plug in 0 and h. If you plug in 0 and h, that number here, 1 over 4 to power 0, non-zero base to power 0 is 1. So this whole thing becomes negative 1. Minus the 2 is minus 3, right? As we found in the process. Okay. All right, so this is the graph of w. If we try to answer the second question now, which is write the domain and range of the function w. Well, what do you think the domain is? This is part B, right? And this thing above was part A here. Okay. So the domain of the function w, what is it, h? Domain of the function h, sorry, I meant here to write w, I don't know why I wrote. Anyway, so let me fix it. I meant here to write obviously h. Okay. All right, back to this domain of h. So the domain of the function h, I mean, no matter what input you give for the x-axis, and from the x-axis, you're gonna always see an output, right? In other words, if you try to flatten the graph of w along the x-axis, you're gonna see all of it. So this is R, and the range of f, or h, the range of h. So how much of the y value, the y-axis, does h allow you to see? What are the levels that h visits? By levels, I mean these horizontal levels, while h visits all levels from minus infinity all the way to -2, excluding -2. It never reaches -2, right? It will never reach this height or this depth. So all heights are visited from minus infinity all the way to -2, excluding -2, correct? So the range of h is minus infinity all the way to -2, open. It reaches all levels less than -2. But once you get to -2, this depth is never reached. Okay. And lastly, write an equation of the asymptote. Well, it's already written, y equals -2, right? So the horizontal asymptote in this case is y equals -2. Okay, let's continue. Here's the next definition. As n becomes large, so as n goes to plus infinity, this expression 1 plus 1 over n to power n approaches a certain number that people refer to as Euler's number. And Euler is a proper name. This is referred to as Euler's number because of the Swiss mathematician Leonhard Euler, who lived between 1707 and 1783, and is denoted by E. And E is approximately this number, 2.71828182845, etc. And let me tell you that E is an irrational number. It's like pi. There's no pattern in the decimal digits. Okay. There's no pattern in the decimal digits. So those numbers are referred to as irrational numbers, and E is one of them. Okay. To kind of convince yourself, take n to be, start by n being 1. If n is 1, you're talking about 1 plus 1 to power 1, so 2, right? So you're talking about 2. And start increasing n. Take n to be now 2, so 1 plus half to power 2. 1 plus half is 3 halves, right? To power 2. You're gonna, the higher n, the higher you take n, the closer you get to this number, right? That's the idea. Okay. And as n becomes extremely large, to infinity, let's say, this number is approaching, or this expression is approaching a number that people refer to as E. Okay. And these approximately this much. This is truncated after a certain number of decimal digits, right? Anyway, so E is a number that's positive and different than 1. It's approximately 2.7. Okay. So as such, I can use it as a base for my exponential function, right? Remember, for exponential functions, you can use any base that's positive different than 1, right? This is the definition. Remember that? As long as the base is positive different than 1, you can use it as a base for the exponential function. Okay? So E, the Euler number that we just talked about below, can be used here. You get E to power x, the exponential function with base E, Euler's number E. And the next definition is going to tell you that that exponential function is referred to as the natural exponential function. Okay. So this exponential function with that special base E is referred to as the natural exponential function. Okay. All right, let's do a few problems. Back to the book. Let's go to the next page, page 7, what is it? 378, sorry, 378. Let's do one of these problems from 39 to 44. How about 40? Okay, we've done close to these. All right, let's do 43. M of x is minus e to power x minus 3. So the question is use transformations of the graph y equals ex to graph the given function. And in this case, number 43, m of x is minus ex minus 3, right? So let's zoom in a little bit. Let's do it here. Page 378. We said number 43. So the function is m of x equals minus ex minus 3. Okay. So I'm going to start from the parent function ex as we said. And since the base is bigger than 1, we're going to have the pink trend. We're going to have the pink trend that we had above, right? We're going to have, this is ex, so it's p. So since the base e is bigger than 1, remember e is approximately 2.7, the trend is going to be the pink one, right? It's going to be the pink one. Okay. All right, back to this. This y-intercept is 1, right? Okay, and the horizontal asymptote is y equals 0. Right, that's the horizontal asymptote. All right, let's get closer now to m by cooking up this term minus e to power x. So let's call this function, say, t of x. It's minus ex. What's the relationship between minus ex and p? Well, this is simply the opposite of p, right? So this is simply the opposite of p of x, correct? So how do you graph the function negative p of x if you know how to graph the function p? You just reflect the graph of p in the x-axis, right? You're multiplying the output by -1, so you're multiplying each output by -1. So you're reflecting in the y-axis and the x-axis, and as such you get this, right? So this point is the reflection of this one, so this is -1, and this whole trend is t, correct? This is t of x. And this line y equals 0, I mean, we're reflecting with respect to the x-axis, which is itself, so it's gonna be its own reflection, right? So that line remains here. So this is the horizontal asymptote so far. All right, so this is the graph of t. Okay, and finally, we want the graph of m, right? So m is this term, all this term, which is t of x minus 3, right? So m is t of x, which is negative ex minus 3, correct? Let me zoom out so you can see it. It's t of x minus 3. All right. And how do you graph t of x minus 3 if you know how to graph t? You just shift down the graph of t by 3 units, right? So you take the graph of t and you shift it downward by 3 units. And remember, that's going to affect the horizontal asymptote, correct? That horizontal asymptote. So here the graph of t gets closer and closer to 0 as x gets closer and closer to minus infinity. Now the graph of m, since these terms, I mean, as x goes to minus infinity, this is going to go to 0, right? Remember? As x goes to minus infinity, this term is going to go to 0, and hence this whole thing is going to go to minus 3, right? So you can say that as x goes to minus infinity now, m of x is going to go to minus 3. Agree with that? And as such, the horizontal asymptote is expected to shift down, right? By 3 units as well. Okay. All right, so this is the horizontal asymptote for or of m, and the graph of m is a shift downward of the graph of t right? By 3 units. So this is the graph of m. And what's this intercept, y-intercept? What used to be -1 now is going to be shifted down by 3. So this is going to be -1 minus 3, so -4, right? Okay. All right, so this is the graph of m then. And the horizontal asymptote is y equals -3. All right, back to the book. The questions were part A, use transformations of the graph. Part B, write the domain and range. And part C, write an equation of the asymptote. So part B, the domain of the function m. Well, as we've said it many times before, the graph of m, if you project all the points of m onto the x-axis, you're going to see all of the x-axis, right? In other words, if you flatten the graph of m along the x-axis, you're going to see all of the x-axis. So no matter where you are located on the x-axis, no matter what input you give from the x-axis, there exists an output for it, correct? So the domain is all real numbers. And the range of m is what? Well, so m visits all levels, right? All the levels from -infinity all the way to -3, excluding -3, correct? So try to project all the points of m onto the y-axis. You're going to see the y-axis, all the y values from -infinity all the way to -3, right? Excluding -3, because this function never touches -3. Because if it were to touch, this means p would have touched 0. But we know this is not the case, so that function m never touches -3, right? So it's going to be -infinity all the way to -3. Correct. Okay. And the last part is they wanted us to write the asymptote, the equation of the asymptote, y equals -3. We've already written this. So it's a horizontal asymptote, right? Okay. Let's go to the book again. Let's go to page 381. How about number 72? So the question is, find the real solutions to the equation this, right? X squared EX minus EX equals 0. So this is on page 381, number 72. So we wanna find all real solutions of the equation x squared e to power x minus ex equals 0, right? Okay. Obviously, the best way to do this is to pause the video and do it on your own first, okay? Even if you struggle, this is how you learn. You learn from your own mistakes. So please stop the video and try to do it yourself. The way I'm going to proceed, I'm going to factor out an EX, and I get x squared minus 1, right? As the other factor, correct? So I get EX times x squared minus 1 equals 0. And x squared minus 1 can also factor as x minus 1 times x plus 1, right? This is a difference of two squares. You can think about x squared minus 1 as a squared minus b squared, because 1 and 1 squared is the same, right? So you can rewrite it as such. Okay. And then look at this equation. How many factors you have? You have 1, 2, 3, right? So you have multiplication between 3 factors. 1, 2, 3. And you know that the result is 0. When does this happen? When can you multiply 3 things, or when can you multiply entities and get 0? This happens precisely when at least one of them is 0, right? So either this guy who's making the whole product 0, or this guy who's making the whole product 0, or this guy who's making the whole product 0. Correct? So at least one is 0. So this is the same as saying then as either the EX is the guy who's making the whole thing 0, or the x minus 1 factor who's making the whole thing 0, or the x plus 1 factor is who's making the whole thing 0, meaning at least one of them is 0, right? Okay. Take a look at this first one, EX equals 0. When can this happen? When can EX equal 0? Remember the graph of EX? It was the pink trend, right? Let me actually graph it in pink. So EX is this guy, right? And the question is, when is it 0? Well, the graph of EX is never 0. It will never get to 0. It's always positive, as a matter of fact, right? This is always bigger than 0 for all x. That's what I mean by always. For all real numbers x. Correct? So there is no x that makes EX 0. So this guy can never happen. This guy can't happen. Agree with that? This guy cannot happen. Why it cannot happen? Because again, look at the graph. EX is always positive. No matter what x is, e to power x is always positive. So it can never be 0. And then the whole thing reduces to either x minus 1 is 0 or x plus 1 is 0, right? Because the first factor is not the guy who's making it 0. That's not the guy who's making the product 0. It's one of the other two guys who's making the whole thing 0, right? And this is easy to continue here. This means x is either 1 or negative 1, right? So, and this initial equation is, I mean, as you see, they're all equivalent, is equivalent to this equation that you see, or compound equation that you see at the end. So what are the solutions of this? They are exactly what you see at, I mean, the last compound statement. Either x is 1 or x is negative 1. So the solution set of that given equation is the doubleton minus 1, 1, right? The set consisting of two elements, minus 1, 1. Those guys, right? Okay. All right, let's continue. How about doing 77? Okay, or 78. Let's do 78. Probably it looks a little more complicated. Let's do 78. So I want to show that this side is equal to this side, right? I want to show that this side is equal to this side for all x. So we want to show that this is actually an identity. It's true for all x. Okay, so let me copy this. So this is number 78. We want to show that for all x, there holds the following: 2 times ex minus e to power negative x divided by 2. So 2 times this factor times ex plus e to power negative x divided by 2 is equal to e twice x minus e negative twice x divided by 2, right? So that's what we want to show. We want to show that the left-hand side and the right-hand side match no matter what x is. Okay. All right, so let's start with this. I want to start from the left-hand side, and I want to write a sequence of equalities, and eventually I'm going to get to the right-hand side. And every step I'm going to use a logical statement that I know it holds for me, right? For example, 2 divided by 2 is 1. I know this, right? 2 divided by 2 is 1. I know this. So I can simplify by 2. Let me highlight this in green here. So I can simplify by 2. And what do I get? I get that the left-hand side is ex minus e negative x, this guy, times the other factor, which is ex plus e minus x, right? All right, you can think about this as ex minus e minus x, the whole thing is over 1. Am I correct? You can think about this whole thing as over 1. And this becomes a product of two quotients. And a product of two quotients, how do you perform a product of two quotients? This is the product of, or this is the quotient of the product of the numerator divided by the product of the denominator, right? So what I'm saying is that this is the quotient of, upstairs is the product of the numerators, so this times this. And downstairs is the product of the denominators, which are 1 and 2. So 1 times 2 is 2, right? Okay. You want to show it's this, right? So technically, this is actually that. Well, the 2 downstairs is promising. Okay, this looks good. Upstairs, apparently, this product is e to power 2x minus e to power negative 2x. Right? So let's make sure that this is the case. What's the form of this? ex minus e minus x times the same ex plus the same e minus x. So this is very much of the form. This is very much of the form a minus b times a plus b. Do you agree with me? If you think about this term as a, that's the same guy, a. And if you think about this term b, that's the same guy, b. So this is of the structure of this expression, the numerator is a minus b times the same a plus the same b, right? All right, and if you FOIL this out, this is the difference of two squares. We've used it above, right? But we used it backwards. This time we use it from top to down. So we're gonna use that. We're gonna use this, obviously where a is ex and b is e negative x, right? All right, as such, what do we get? A squared, what's a squared? It's ex squared, right? Minus b squared, and who's b again? Is e negative x. So you get this, right? Makes sense? Keep an eye on what you want. What do you want again? You want this. Can you convince yourself that this is the case? Can you convince yourself that this is the case? Use one of the properties that you know of exponents, right? This is of the form an exponential expression raised to a power. What do you do with the powers? You multiply them out, right? You keep the base and you multiply the powers. Very similar, similar discussion applies here. You keep the base and you multiply the powers. This is where these guys come from. Correct? So the last step is immediate. So this is going to be e twice x minus e minus 2x, right? E power negative 2x, because minus x times 2 is negative 2x. X times 2 is 2x, right? So you get exactly the right-hand side as desired. Make sense? Okay. All right. Let's do one more problem. Let's do one of these two problems, 79 or 80. Let me do 80, the even, because you guys have the solution for the odd. So we want to find the difference quotient, f of x plus h minus f of x over h, and we want to write the answers in factored form, where f of x is 2 to power x. Okay, so this is number 80. So we want to find the difference quotient f of x plus h minus f of x divided by h, where f of x is the exponential function with base 2, right? 2 to power x. Okay, so what is this guy then? So this quotient, f of x plus h minus f of x divided by h, is equal to, what's f of x plus h? Well, f of anything is 2 to power that thing, right? All right, let me replace this by an asterisk. Let me mask that guy x. F of an input is 2 to power that input, right? And here, who's my input? X plus h. So who's going to take the role of the asterisk? Is the x plus h. So that's going to be 2 to power x plus h minus f of x, which means 2 to power x divided by h, right? Agree with me? All right, if you go back to the question, they said write the answers in factored form, right? So write the answer in factored form. So we found it. We found the difference quotient. Write it in factored form. The best we can do is to factor out. Look at this. Upstairs. Upstairs, isn't it the same as saying 2 to power x times 2 to power h for the first term minus the second term? What did I do here? I used one of the properties of exponents. Probably you're more accustomed to do it backwards. What is this? The product between two exponential expressions having the same base. What do? So you're multiplying two exponential expressions with the same base. You keep the base and you add the powers, right? Keep the base and you add the powers. So I used it in this direction now. And this is x, right? Okay. I did a mistake here. I copied it wrong. This is x. Why it's x? It's this term, right? That term is this term. Okay. So one more time. This guy, I can split it as such. As we said, you're probably more familiar to go backwards. You keep if you're multiplying two exponential expressions with the same base, you keep the base and you add the powers. So this is this, and 2 to power x is that guy. Divide by h, right? All right. And here, I hope you see that I can factor out 2x as I told you. And we get 2 to power x times 2h minus 1, right? Divide by h. Agree with me? You can distribute the multiplication over subtraction and check that we get back that guy. 2x times 2h is this guy, minus 2x times 1 is minus 2x, correct? All right, so we answered the question, and this is the end of this section.